Hey there, physics fans, and welcome to a cosmic ride that just might shake your understanding of the universe. We're about to tackle a big one: energy conservation. You know, that fundamental principle saying energy can't be created or destroyed, only transformed? Yeah, that one. Turns out it's not as ironclad as they've been telling you. For centuries, energy conservation has been the darling of physics, as comforting and reliable as a warm cup of cocoa on a cold winter's night. It's the backbone of everything from the mundane, like your refrigerator keeping your drinks cold, to the mind-bogglingly massive, like stars burning for billions of years. It's the law that just makes sense, right? Well, strap yourselves in because we're about to venture into the realm where things get a little messy, where the seemingly unshakable pillars of physics start to wobble and even energy conservation itself takes a hit. Don't worry, it's not as scary as it sounds. Okay, maybe a little scary, but trust me, it's way cooler than scary. Before we dive into the deep end, let's get back to basics. Energy, as we usually think of it, comes in a bunch of different flavors: kinetic, potential, thermal, you name it. And the beauty of conservation is that no matter how wildly energy might transform between these forms, the total amount always stays the same. It's like a cosmic game of musical chairs, where the chairs themselves might change shape, but there's always a seat for every player. At least that's what they told us. Enter Noether, a mathematical genius who rocked the world of physics in the early 20th century. Noether's theorem connected conservation laws to symmetry. For every continuous symmetry, there's a corresponding conservation law. Rotational symmetry, for example, links to the conservation of angular momentum. Noether's theorem also helped discover new conservation laws, provided the laws of physics are symmetrical. Einstein's theory of general relativity would soon challenge these assumptions. Energy follows the rules, playing nice with symmetry, but then quantum mechanics arrived and all bets were off. In the quantum realm, classical physics gets thrown out the window. Energy starts acting like jittery particles, popping in and out of existence. You might think a vacuum is just empty space, right? In the quantum world, empty is a relative term. Even the vacuum is teeming with virtual particles, borrowing energy and paying it back quickly. These fluctuations cause the Casimir effect, where two plates in a vacuum attract each other. Is it really breaking energy conservation? It's a bit of a head-scratcher. They borrow energy and pay it back so quickly it's almost like they never borrowed it. It's like a cosmic game of hot potato with tiny packets of energy. Just when you thought it was safe to go back into the physics lab, the universe decided to throw another curveball expansion. And not just any expansion, but an accelerating one. According to Einstein's theory of general relativity, the fabric of spacetime itself isn't static but rather a dynamic, ever-evolving entity. Observations revealed that this expansion is speeding up. The culprit? Dark energy. We don't know what it is exactly, but it makes up 70% of the universe's energy density. And as the universe expands, the total amount of dark energy increases. Alright folks, buckle up, because we're about to enter Einstein's cosmic playground where gravity isn't just a force, it's the architect of reality itself. See, in Einstein's general relativity, space and time aren't just a static backdrop for the universe's grand play. They're active participants in the drama, warping and curving in response to the presence of mass and energy. Think of it like a trampoline. If you toss a bowling ball onto it, the trampoline will sag under its weight, right? That's kind of like what massive objects do to space-time. They create these little dips and curves, and anything that ventures too close, even light itself, gets caught in the cosmic swirl. Now you might be thinking, okay, that's cool and all, but what does it have to do with energy conservation? Well, hold on to your hats, because here's where things get really interesting. In general relativity, energy isn't just about the stuff moving around within space-time. It's also about the very fabric of space-time itself. It's like the universe is playing a cosmic game of double-entry bookkeeping, keeping track of both the energy of matter and the energy stored in the curvature of space-time. And here's the kicker: because space-time can warp and curve, so too can the energy it contains. It's like trying to balance a checkbook on a roller coaster. The numbers just never seem to add up quite right. Suddenly, that comforting, predictable world of classical physics, where energy was always accounted for, starts to feel a million light-years away. Now, gravity, being the mischievous trickster that it is, has a few more surprises up its sleeve. One of the most mind-bending is gravitational redshift. Imagine shining a beam of light from a neutron star. As it climbs out, it loses energy, shifting towards the red end of the spectrum. It's like the light is paying a cosmic toll in energy. The energy goes into the gravitational field itself. Gravity snatches energy from photons, stashing it away. And if you thought gravitational redshift was weird, wait till you hear about black holes. These cosmic monsters take gravity's energy-bending antics to a whole new level. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape their clutches. They're like the ultimate cosmic Roach Motel's energy checks in, but it never checks out. Now, you might think that black holes are just giant cosmic vacuum cleaners, sucking up all the energy in their vicinity. But it's actually a bit more complicated than that. See, when matter falls into a black hole, it doesn't just disappear, it adds to the black hole's mass, and therefore, its gravitational pull. It's like the black hole is bulking up on a cosmic treadmill, converting the energy of infalling matter into more gravity. And because gravity itself carries energy, the total energy of the universe remains, well, that's the million-dollar question, isn't it? See, the problem with black holes is that they represent a singularity in spacetime, a point where our current laws of physics break down. It's like trying to read a page torn from the middle of a book. You can see that there's a story there, but you're missing crucial pieces of the narrative. Section 4, The Curious Case of Cosmic Inflation. And as if black holes weren't mind-bending enough, let's talk about cosmic inflation. This theory, proposed in the early 1980s, suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, ballooning from a size smaller than an atom to something closer to a grapefruit in the blink of a cosmic eye. It's like the universe went through a growth spurt on steroids fueled by a mysterious form of energy called the inflaton field. Now, inflation is a really cool idea because it solves a lot of problems in cosmology, like why the universe looks so smooth and uniform on large scales. But it also raises some really interesting questions about energy conservation. See, during inflation, the energy density of the universe remained constant even as the volume of space increased exponentially. That means the total amount of energy in the universe must have increased by an unimaginable amount, seemingly out of thin air. It's like the universe wrote itself a blank check and then cashed it in for all the energy it could ever need. Now, some physicists argue that this violation of energy conservation is only temporary, that the energy borrowed during inflation was somehow paid back when the inflaton field decayed, giving rise to the particles and forces we see today. But others suggest that maybe, just maybe, energy conservation isn't as fundamental as we thought, that the universe has a few more tricks up its sleeve. Section 5, A Universe Redefined. So, where does all this leave us? We've journeyed through the warped landscape of general relativity, explored the energy-bending antics of black holes, and pondered the cosmic blank check of inflation. And along the way, we've glimpsed a universe far stranger and more wondrous than we ever imagined. A universe where even our most cherished laws of physics might not be set in stone. Now, before you go tossing out your physics textbooks and declaring the universe a free-for-all, it's important to remember that energy conservation is still an incredibly useful concept in most everyday situations. Your refrigerator isn't going to suddenly stop working because of quantum fluctuations, and the Earth isn't going to spiral into the sun because gravity decided to take the day off. But on the grandest scales, in the realm of black holes, galaxy clusters, and the expanding universe, the rules of the game might be a little more flexible than we thought. Maybe, just maybe, energy conservation isn't the absolute, unwavering law we once believed it to be. Maybe it's just a local approximation, a useful rule of thumb that works well in our little corner of the cosmos, but breaks down in the face of the universe's most extreme phenomena. And if that's the case, it opens up a whole new world of possibilities, a universe where the seemingly impossible might not be so impossible after all. Section 1, Quantum Fields, where energy gets real and unreal. In quantum field theory, we ditch particles as tiny billiard balls and embrace fields. Imagine a cosmic ocean of energy, constantly in motion, rippling with quantum possibilities. These ripples are quantum fields, the fundamental building blocks of reality. Just like the ocean has waves, these fields have excitations we perceive as particles. You might think empty space is a cosmic chill-out zone, but you'd be wrong. Even the vacuum is teeming with activity, a bubbling cauldron of virtual particles. These virtual particles have real, measurable effects like the Casimir effect. They operate on borrowed time and energy, constantly winking in and out of existence. It's like the universe is running a massive cosmic tab. Amidst the sea of virtual particles, there's the Higgs field, crucial to our understanding of the universe. The Higgs field gives mass to particles, from electrons to the Higgs boson. Think of it as cosmic molasses. Particles interact with it to gain mass. The Higgs field has a non-zero energy, contributing to the universe's energy density. It's like the universe's own personal energy drink. The Higgs field plays a crucial role in the existence of virtual particles. Virtual particles pop into existence, borrowing energy from the vacuum. They annihilate each other, returning energy to the void. The Heisenberg uncertainty principle allows this without violating energy conservation. It's like they're sneaking past the cosmic bouncer. We've journeyed through quantum foam, met the Higgs field, and seen virtual particles. The universe is far stranger and more uncertain than we imagined. Energy conservation isn't completely out the window. Our understanding is evolving. There might be a deeper principle at play, encompassing both matter and vacuum energy. The universe is full of surprises, making exploring the cosmos exciting. We're embarking on a journey to the edge of the observable universe. Edwin Hubble discovered galaxies moving systematically away from us. The expansion of the universe is like space-time stretching, not an explosion. Every point in the universe sees every other point moving away. This explains the observed redshift of distant galaxies. You might think expansion would slow down, but it's speeding up. Observations of distant supernovae revealed the universe's acceleration. It's like a cosmic turbocharger causing faster expansion. This discovery earned a Nobel Prize and forced physicists to rethink assumptions. The universe's acceleration remains a cosmic conundrum. Dark energy is driving cosmic acceleration, but we don't know much about it. It doesn't interact with light or matter, only through gravitational effects. As the universe expands, dark energy's density remains constant. This seems to contradict energy conservation, like a cosmic blank check. Physicists are left wondering about the universe's cosmic accounting. Some physicists argue energy conservation is an illusion, a trick of perspective. Maybe energy is conserved on a deeper level, but we lack the right equations. Others propose energy conservation isn't as fundamental as we thought. The universe might be borrowing energy from an unknown source. This opens up new possibilities for understanding the cosmos. We've journeyed to the edge of the observable universe and encountered dark energy. The cosmos is far stranger and more wondrous than we imagined. These are open questions, areas of active research. The expanding universe and dark energy force us to confront our knowledge limits. Exploring the cosmos is exciting because of these mysteries. The Higgs boson is evidence of a cosmic conspiracy, breaking symmetry to create mass. The Higgs field, in its lowest energy state, gives mass to particles. In the early universe, the Higgs field was in a different state. As the universe cooled, the Higgs field underwent a phase transition. This transition released energy, giving rise to the mass of particles. Now let's talk about those mischievous virtual particles again, those quantum fluctuations that seem to pop in and out of existence with a blatant disregard for the cosmic budget. You see, these virtual particles aren't just some theoretical curiosity. They have real measurable effects on the energy density of the universe, effects that have physicists scratching their heads and wondering if the universe is running some sort of cosmic shell game. One of the most striking examples of this is the Casimir effect, which we touched upon earlier. In a nutshell, the Casimir effect says that two uncharged, perfectly smooth plates placed very close together in a vacuum will experience an attractive force. Why? Because the quantum vacuum between the plates is teeming with virtual particles constantly popping in and out of existence. Now, these virtual particles can have any wavelength, but the ones that can't fit between the plates are suppressed, kind of like trying to stuff a giant beach ball into a tiny mailbox. This creates a difference in the energy density of the vacuum inside and outside the plates, resulting in a net inward pressure that pushes the plates together. It's like the vacuum itself is playing a cosmic prank, whispering to the plates, "Hey, come a little closer and let's see what happens." And what happens is that the plates actually move, a tangible demonstration of the energy inherent in the quantum vacuum. But perhaps the most perplexing example of energy conservation's apparent breakdown comes from the realm of cosmology, where dark energy reigns supreme. This mysterious force, which makes up roughly 70% of the energy density of the universe, seems to be driving the accelerated expansion of spacetime, pushing galaxies apart at an ever-increasing rate. Now, here's the kicker. As the universe expands, the density of dark energy remains constant. That means the total amount of dark energy in the universe is actually increasing over time, like a cosmic credit card with no spending limit. It's enough to make even the most seasoned cosmologist reach for a stiff drink. So, where is all this extra energy coming from? That's the million-dollar question, and physicists are still scratching their heads trying to figure it out. Some speculate that dark energy might be drawing energy from the quantum vacuum, like a cosmic vampire siphoning energy from the void. Others suggest that maybe, just maybe, energy conservation doesn't apply on the grandest scales of the universe, that the universe has a way of balancing its books that we haven't yet grasped. Section 4. The Cosmic Budget, Balancing the Books, or Not. So is the universe running a cosmic deficit, constantly borrowing energy from some unknown source? Or is there a deeper principle at play, a cosmic accounting trick that we haven't yet uncovered? The truth is, we don't know. Energy conservation, a principle that has served us so well in our everyday lives and scientific endeavors, seems to be on shaky ground when we confront the universe's most extreme phenomena. Perhaps our definition of energy itself needs to be revised, expanded to encompass the energy of the quantum vacuum, the energy of spacetime itself, the energy of realms beyond our current understanding. Or maybe, just maybe, the universe doesn't have to balance its books in the way we expect, that it's free to borrow and spend energy in ways that defy our current comprehension. It's a humbling thought to be sure, but one that opens up a universe of possibilities. Section 5. The New Frontier, Embracing the Unknown. So, where do we go from here? Do we abandon energy conservation altogether, relegating it to the realm of classical physics curiosities? Not necessarily. Energy conservation is still an incredibly useful concept in most everyday situations. Your phone isn't going to suddenly stop working because of dark energy, and your coffee isn't going to spontaneously boil because of vacuum fluctuations. But on the grandest scales, in the realm of black holes, galaxy clusters, and the ever-expanding universe, we might need to embrace a more flexible, more nuanced understanding of energy and its conservation. This isn't a sign of defeat, but rather a call to adventure, an invitation to explore the universe's most perplexing mysteries with open minds and a healthy dose of curiosity. The universe is full of surprises, and the more we learn, the more we realize how much we don't know. And that, my friends, is what makes exploring the cosmos so darn exciting. So there you have it, folks. We've journeyed to the edges of physics where energy, that seemingly reliable cosmic currency, starts playing fast and loose with the rules. We've seen how general relativity warps the very fabric of spacetime, how quantum mechanics throws a cosmic rave in the vacuum, and how dark energy fuels the universe's insatiable expansion. It's enough to make you wonder if the universe is running some grand cosmic shell game, shuffling energy around like a seasoned card sharp, leaving physicists scratching their heads and rewriting textbooks in its wake. But hey, who are we to judge? The universe has been around for about 13.8 billion years. it's had plenty of time to master a few tricks. The truth is, our understanding of energy, and how it behaves on the grandest scales, is still very much a work in progress. We've clung to the principle of energy conservation for centuries, and for good reason. It served us well in countless scientific endeavors, from building bridges to launching rockets. But when we peer into the cosmic abyss, when we confront the mind-bending realms of black holes, quantum foam, and the accelerating expansion, the old rules seem to blur, the lines between creation, destruction, and transformation becoming as fuzzy as a cosmic ray hitting a particle detector. Our grasp on the universe is slipping through our fingers like cosmic dust. Embrace the mystery. The universe isn't obligated to fit neatly into our preconceived notions. These cosmic curveballs are a testament to the universe's boundless creativity. We're like kids staring up at the night sky, filled with wonder. What happens inside a black hole? Is our universe just one bubble in a cosmic sea of multiverses? These questions drive cutting-edge research in physics today. Scientists are building bigger telescopes and designing more sensitive detectors, all in the hopes of deciphering the universe's enigmatic whispers. So what does it mean to live in a universe where even energy, that seemingly fundamental building block of reality, might not play by the rules? Does it mean that all bets are off, that anything goes? Not quite. The universe, for all its weirdness, is still a remarkably consistent place. Apples still fall from trees with predictable acceleration, stars still burn for billions of years, and your phone still, mostly, works the way it should. But it does mean that we need to be open to the possibility that our current understanding of physics, while incredibly successful in explaining a vast range of phenomena, might not be the final word. It means being willing to question our assumptions, to consider ideas that seem counterintuitive, even heretical. It means embracing the unknown, not with fear, but with a sense of awe and excitement. After all, it's at the frontiers of our knowledge, where the familiar gives way to the strange, that the most exciting discoveries are made. It's like exploring a new city, venturing beyond the well-trodden tourist paths, stumbling upon hidden alleyways and unexpected vistas. You might not always know where you're going, but that's part of the adventure. So, let's raise a glass to the universe, to its boundless creativity, its penchant for breaking the rules and defying expectations. Let's celebrate the mysteries that still elude us, the questions that keep us awake at night, for they are the fuel that drives our curiosity, the spark that ignites our imagination. The universe is a vast and wondrous place, a cosmic dance of energy and matter, of creation and destruction, of order and chaos. And we, my friends, are privileged to be a part of that dance, to witness its unfolding splendor, to unravel its deepest secrets. The journey is far from over, but one thing is certain: the universe will continue to surprise us, to challenge our assumptions, and to remind us that even in the face of the unknown, there's always more to learn, more to explore, more to discover. So, keep looking up, keep asking questions, and never ever stop exploring the cosmos. The universe is vast, but it's not indifferent. It's waiting for us to catch up, to join the cosmic dance, and to unravel its most profound secrets. And who knows? Maybe, just maybe, we'll find that the universe has been saving its most spectacular performance just for us.